Okay, yeah, I guess we can start. So, oops. Okay, so let's see. Which is today's class? Today's lecture 13. So, so today we're again going to start like talking more like carefully about this situation of probability in the continuous case. Again, the basic like idea or model to keep in mind, or like analogy or situation, is one where like you know you have like the position of a particle, but maybe its value is like unknown or random, in the sense that there's like a certain probability of the particle being located somewhere. Uh, but now, like as opposed to before, where like it was only in infinitely many, you only care about whether like the particle was in a specific box, which there were like a finite number of. Now you care about like more like in the continuous situation, where like the particle, just the probability of the particle being somewhere on a given interval. Okay. The thing is, like, it didn't make a lot of sense per se to talk about the probability that the particle is exactly at a given number, or like at a given distance, for example, from the origin. Um, at least not for what we'll be most interested in. Um, if you wanted to do that, you need like what's called like a direct delta function. But for us, like you cannot. It's not convenient to do that. So we want to think kind of like that. It's better to think, well, in any case, for practical purposes, that you can never specify the position of a particle or of any continuous quantity like with a complete knowledge, because there's usually like like always some uncertainty on whatever instruments you're using to measure those values. So like it already makes sense, even from an experimental point of view, to just like think that you're going to specify things up to a certain range. So like the analogy here was to just think that, well, maybe you don't specify x, but only x like within like some amount delta x from it, or that delta x over 2. Okay. Again, for a mathematician, like delta x can be as small as you want. In the real world, like there will be limitations for how good delta x can be specified, but that's okay. So that is something that we can try to assign a probability to. So we will try to assign like a probability to like the position of the particle, for example, being in this interval and things like that. And so the discussion that we've ended up with last time was just that because you're kind of in the continuous case, um, what makes most sense is just to think about it as an integral, um, to compute these probabilities. And so that's this is actually the formula that we were thinking about last time. So that's kind of like the how we will start taking that would be like our starting point for discussing continuous probability. So let me just give you that. So for today, so what would be continuous probability? Or let me put it like this: probability when the random variable can take a continuous set of values. Like, Well, in this case, like again, we'll think about this probability as being specified by what's called a probability density function. So this is going to be specified by what is known as a probability density function in a PDF then. So, and that's I mean, this is kind of usually the name that's it's given to it. So it it's just going to be a function again because of our expectation that probabilities are non-negative numbers. To is basically what you all assume is that it is a non-negative function. So f of x, like basically there are two uh, properties that you ask. So f of x is going to be non-negative for each x. So it's greater or equal to 0 all the time. And so this is the first property. No, the second property more like is more like the notion that we want this to work as a probability. The interpretation that we will give to this f of x is that the probability, this is what I wrote like at the last step last time, that the probability that uh, the random variable x is between certain two numbers is literally just the integral of this probability density function. So this is how we are going to compute these probabilities. Okay. So again, like maybe I'll write in words what this means. This is the probability that the values x the probability that the values of x will be between x1 and x2. And the last one is the kind of like the most, well, not the most important, but what makes this uh the probability enter into like our considerations, because up to this point, like you're just kind of talking about integrals. So the last condition is kind of saying that if you remember in the discrete case, in the discrete case, you always have like this constraint or this condition that like the probabilities for all the different outcomes should add up to one, right? So the analog of that, again, if you think about replacing the sum with an integral, is kind of that x, like the random variable must take a value somewhere, but somewhere can now go from like, negative infinity to infinity. So the normalization condition, that's how it's called. And I'll put it with a different color to just emphasize this. Is that the integral from negative infinity to infinity of f of x dx equals 1. So that means that x must take values like at some, that it's kind of like saying the values of x must be located somewhere on the real line, right? It's more or less what that is saying. Right, because it's just like the probability that x is between negative infinity and infinity. So that kind of makes sense. Like the values of x must lie somewhere. So it's just saying that the values of x will must be somewhere on the real on the number line of the real line on the number line with certainty. Is that okay? So you'll see in a bit. It's not that so sometimes we work with this improper integral. Sometimes like the interval will just end up being a finite interval because you kind of declared the density function to be zero outside the interval. So you don't really have to do the integral from negative infinity to infinity. But it's more elegant to just write it from negative infinity to infinity to begin with, and then in a specific situation you just focus if the density function is defined just on some interval, then you just like do that. That making sense. Questions about this up to this point? So let me give you a quick example, which is kind of the easiest example that you could define. This is the analog of the fair die of saying that every sign must be equally likely. So the analog of that is called the uniform distribution. So let's talk first about the uniform distribution. So it is this is like the analog of a fair die or a fair coin, or any situation where like all the probabilities have the same value, where every outcome is equally likely. So any situation where all the probabilities have the same value. So what the idea would be here is like uh and you'll see in a second that this one only works for finite on a finite intervals. So imagine that you have like a finite interval. You can call it A to B. So this one is actually finite. So let's see. Let me put a different color. Okay. So imagine you have like a finite interval, A to B, and you have like the particle, right? But you don't know where the particle is located, right? So in that sense is why it's random, right? So the idea like the uniform distribution is like imagine that somehow you choose like the midpoint here between A and B, right? Like half the distance. So like this interval has the same length as this interval. So in the uniform distribution, you would like to say that the probability for the particle to be on the left half is 1/2, right? Because it's just half the interval. Is that making sense? Or the probability for the particle to be on the right interval is also 1/2. Okay. Or like imagine that you break the interval into a you know you break the interval into 4 pieces. So 1, 2, 3. I mean, I guess like you can see them here more or less. Well, let's say 3 because it's easier for me to draw it right now. So like if you break the interval into 3 pieces, if each piece is of the same length, you would like to say that the probability for the particle to be in one of those intervals is at 1/3. Okay, so it's kind of like the idea of the uniform distribution is kind of just to make the probability of finding the particle on a particular interval just proportional to the length of that interval. Okay, so the idea of the uniform distribution is to make, let's say this is like an interval x1 to x2, to make this probability proportional to the length of the interval x2 minus x1, which is, I mean, which is is the idea making sense? So it's kind of like it's kind of like the best way to kind of give equal importance to every point on the interval. Again, you cannot assign a probability to a single point on the interval, but you can say that that for sub intervals of the larger interval, they should only count, they should appear in the same, they should be weighted in proportion to how big they are. And so it's kind of like the most symmetric thing you could do. Only the length matters in determining this distribution. Is that okay? Is that making sense? So I'm just trying to say that I want this to be like some constant times x2 minus x1, where c is a constant. Is that okay? So far, so good. Questions about this up to this point? So how could you find first, like the first thing that you have to ask is how would you find this constant, right? How to find the constant. And this is where you have to use, like this is where we do need the interval to be finite, because if the interval is infinite, like then the length of an infinite interval is by almost circularly infinite, right? So you cannot like make it proportional to the length because you'll get like an infinity somewhere. But if the interval is finite, right? Imagine that the particle can really only be inside this interval, right? So let's say that the particle or x can only take values between a and b. So what should this probability be based on what I just said? What should be the probability that x is between a and b? You are jumping a little bit ahead because that will be the probability density function, which is not quite the same as just like the probability itself. That, I mean, it's related to this answer, but here I'm just asking for the probability itself, which is slightly different from the probability density function. So this is just like saying, like, I know the particle is always between A and B. So what should be the probability that the particle is always between A and B? It should sound like a circular question. Uh, so it should just be one, right? Like the probability itself. Um, Is that making sense?
So essentially, like all the values are between A and B. Is that why the probability is just going to be one?
Correct. Yeah, you're by assumption you're just assuming, like, imagine you had like the clearest example of this is like this gas containers, right? Like, so you have like these thermodynamic problems where you have like a gas inside a container with impenetrable walls or whatever, right? So you know for certainty that the particle is somewhere inside that container, right? So that forces like the locate that collapses the position of the particle from being to negative infinity to infinity to just like within the length of that container. Is that making sense? So it's kind of like building like, you know, impenetrable walls. Like, so right, that's like why this probability would be equal to one. So here I'm really using that x can only take values between A and B. Like, it's important to have that into the assumption. So why is that important? Because then these, like, based on my requirement that that in general this probability should be proportional to the length of the interval, this should just be C times B minus A, right? By my requirement of what the uniform distribution should be. So that gives you like the value for C. So the value for C should be 1 over B minus A. That comes, so this 1 over B minus A, that's how it appears in this context. Okay. So the probability that X is between X1 and X2 is really X2 minus X1 over V minus A. Okay. Is that making sense? So like this B over V minus A is kind of like a normalization, what we would call like a normalization factor. It's just some ratio that you'd have to take in order to guarantee that this gives you one if you plug in the condition that something has to happen. Okay. But then this at the same time, you want this to be equal to the integral from x1 to x2 of f of x dx, right? And well, this is where like you have to remember your calculus knowledge, right? When would you get like, I mean, for what sort of function could you get something like this, where like, you know, the value of the definite integral is just essentially it's basically the endpoints up to a constant, right? So for what type of function would you get like what sort of like function would you have that has this property that if you integrate it from x1 to x2, you just get x2 minus x1 over b minus a. Yeah, exactly. 1 over b minus a. Yes. Good. So this is like the probability density function for the uniform distribution. So on the interval, so it's 1 over b minus a on the interval um, a b and 0 outside it. So if you want to think about its graph as a function of x, here's x, here's like the interval AB. Let's put it somewhere. I don't want to make it biased. So let's say the interval is kind of like for both of positive and negative values of x. And the uniform distribution is just, the graph looks like, it's just like the equation of a horizontal line between A and B, right? With value 1 over B minus A. And it just drops to 0 outside of it. It's kind of like saying that, you know, the probability outside for the particle to be outside the walls is exactly 0. So this is a graph of F uniform. Is that making sense? So it is like the analog of saying that all the outcomes are equally likely, uh, because it's kind of like you're giving the same weight or contribution to every point on the interval AB. Is that you cannot just do it by giving every point like a finite probability. What you do is kind of like saying that each sub piece of that interval, each sub interval contributes a probability proportional to its length. That's kind of like the version the version of like giving every outcome a finite the same probability, saying like, well, the outcome is the probability of the interval is just proportional to the probability of the sub interval is just proportional to the length of that sub interval. Is that okay? Questions about this so far so good? Okay, here's another cool trick, a calculus trick. So there's an finite interval. No, well, in fact, almost in general, there's like a very nice way to kind of create these probability density functions. So here's like a cool trick. Here's a trick to find probability density functions. Start with your favorite non-negative function in the world. Um, for which for which oh, let me call it I cannot call it f of x. I'll call it mm, f tilde of x. So it's a silly notation, but like for which the indefinite integral exists. And my claim is that define f of x as f tilde of x divided by what? This value for the improper integral. Then these will define a probability density function. Is that making sense? Um, let's check why that would be true. Well, maybe before doing an example, okay. I mean, before explaining what this is true in general, let's just do it concretely with an example. So, someone give me their favorite function. Okay, I like this function, but we'll have, okay, this is fine. Okay, we'll have to fix it in a second, but this can work more or less. Right, this is e to the x. I like that function, but the problem with e to the x is that, the improper integral does not exist, but it has an issue that the improper integral, right, of e to the x, right, this is infinite. Well, that would be better, and actually we'll spend a lot of time today on that one, but we can still fix fix e to the x a little bit. So in fact, we can let me fix it in two ways. Like first, like one way to fix it is just the problem with the exponential is that it has it has growth, it grows infinitely fast in one direction, right? That's why the proper integral cannot exist. What you can do instead is like kind of modify it a little bit. Sometimes it's nicer to work with positive numbers. So to make it work with positive numbers, I'll work with e to the minus x, because e to the minus x is going to go to 0 as x goes to infinity, right? So I'm going to make it e to the minus x, and just to make this in order to make this normalization condition have some meat to it, I'll write it as e to the minus lambda x for x greater or equal to lambda, and I'll write it as 0 for x negative. Okay, so how does this look? So here lambda is a positive constant. Positive constant. Okay. So how does this graph look like? Well, so I'm declaring it to be 0 before for negative values of x. I have to make it 0 somewhere. So it's 0 for negative values of x. And at 0 is value 1, and then it starts it starts decreasing quickly as an exponential, so it looks something like this, I guess. Right, this is more or less the graph of f tilde of x. Is that making sense? Uh, Again, like lambda, I'm just taking it to be positive constant. So like the growth, I mean, it is going quickly to 0, right? Exponentials, like with is what you would call exponential decay, right? Like this is like a perfect example of what you typically call exponential decay. So this is like has a chance of being of having like a improper integral. So what's the value for the improper integral here? Well, again, like this actually no longer needs to start at negative infinity, because we kind of made it 0 by force before a negative value. So actually you can turn this as an improper integral from 0 to infinity. Right? That's the only thing that really matters for this integral. And what's the value for this integral? It is what? Is it e to the minus lambda x over negative lambda? Is that correct? Oops. Yeah, it looks fine because and this has to be evaluated at x equals 0 and x equals infinity, right? So it vanishes at infinity, right? And at 0, it just gives you, I mean, minus minus, right? When you evaluate, so you just end up getting 1 over lambda. Is that okay? So the value for this integral is 1 over lambda. So far, so good. And so the claim is that these, like as it stands, wouldn't have a chance of being a probability density function because it doesn't integrate to 1. And again, we want the probability of the particle. Again, if you still think of x, like the random variable, as representing the position of the particle, we want the probability of the particle being somewhere to be 1. So that's why you do the normalization trick. So you do the normalization trick. which is just define f of x as f tilde of x divided by the integral. So f of x in this case is, I mean, if you want to see it explicitly, it's lambda times f tilde of x. So it's 0 if x is less than 0, and lambda times e to the minus x if x is greater or equal to 0. My lambdas can start becoming close to x, so I'll try to make it more clear to distinguish them. So what I'm saying is that this will integrate to 1. I mean, like, you kind of build things, like, you kind of made it by force to have like an integral of improper integral of 1, right? Because literally you are dividing by the value of that integral. So this does have like you know, this integral will be 1 by default, right? Because this lambda just basically multiplies the 1 over lambda, and they cancel out. And so what this is saying is that then you could compute the probabilities, you know. So what this is saying is that the probability for the random variable to take values between x1 and x2, let's say that they're both you know, non-negative, because so otherwise it would be a little bit silly, because we already know that it never takes negative values, right? So these, it would be the integral from of this thing. And it gives you right? Is that correct? So the probability, again, let me emphasize this. So the probability, for example, for the particle to have position between x1 and x2, if both x1 and x2 are positive, would be this one. Is that making sense? So in fact, let me see if I can plot it for you on GeoGebra. Give me a second, and I'll show you how it looks. So let's see. I can define a slider. This would be like the value for lambda. It's just, I'll call it a, because it's easier to do that on GeoGebra than to write lambda. And so if x is greater than 0, the probability density function was a times e to the minus a times x. Hopefully this works. Okay, so there you go. Right? So this is kind of giving you oh yeah, and here then I can change the value for, you know, I can change the value for lambda, right? So this is how f of x looks like. So you see, like, it has a decay regardless of the value for lambda, or for a in this case. It does decay, so that means that it becomes more and more unlikely for the particle to be, you know, the particle has like a higher probability of being like near the origin in this case. Like like the probability of the particle being like far from the origin decays exponentially fast. Okay. Is that making sense? So and later, I mean, I can give you the formula for the expected value. There's like an analog formula for the expected value for these things, and so I think the expected value for this one was lambda, if I'm not mistaken. It's lambda or 1 over lambda. That's something that it's easy to check doing the integration. But but like again, like the picture of the probability density function is kind of like that. Is that okay? Any questions about this? In fact, like maybe let me give you the formula for the expected value, um, and the variance of a random variable in the continuous case, because it is essentially what you would have expected um to happen, but just a continuous version of that. So for like so yeah, let's write it down here. So here are some basic formulas. What's the average value or the expected value or the first moment, right? Like they're all called the same, average or expected value or first moment, right? Or the mean, that's another name, right? Again, it has so many names. It is mu of x, mu of x, or mu, or also e of x. That's like those are the most typical names for the expected value. Sometimes you will also find like the bar, although I think that's more common when every outcome is equally likely. But again, these are kind of like the typical names for the expected value. That's literally just like the integral from minus infinity to infinity of x times f of x dx. Or yeah, let me write it like that. And you should compare this with the formula in the discrete case, which was just like the sum of equals 1 to I of xi pi, right? So it's kind of like in a sense like the most straightforward continuous version of that you could make. Okay. Is that making sense? So it is like, yeah, it's not like, you know, it's relatively reasonable, and it is not like a difficult integration problem. Like, yeah, like how was p plus a over 2. So for example, for the uniform distribution, I won't do it directly because it's kind of like nice for you to try it because it's just like a simple integral in calculus. But so for the uniform distribution for f uniform, which is 1 over b minus a, the expected value or the first moment in this case would be like, again, the integral of x to infinity of x times f uniform of x dx. But that's just like the integral from a to b of x 1 over b minus a dx. And that's not too difficult to find. That's just b plus a over 2, if I'm not mistaken. So right, because you get x squared over 2, which is b squared minus a squared. You use the difference of square formulas. So that's how you cancel the b minus a in the denominator. And yeah, which is just the average between the values a and b, right? So it does make sense to call this a uniform distribution. So you can check this. But it is saying that for the uniform distribution, the expected value is just literally the average of the endpoints, right? Which that does make sense. Is that okay? And then yeah, for the I mean, you could also try it for the one that we just did. I just tried to find on the book the name that they gave to this one. I think it was called like the exponential yeah, like exponential random variable with parameter lambda or something like that. Ah, yeah. Yeah, it's actually done in the book anyways. So, but you can double check it. It's, if you want. So for the other one, for f of x, which is lambda e to the minus lambda x for x greater or equal to 0, or 0 for x negative. right? You can check in this case that the expected value, which would be the integral from 0 to infinity of lambda x e to the minus lambda x, in this case, it was 1 over lambda. Here, you will have to use integration by parts at some point if you want to do this. Okay, so one option is to do integration by parts. That's what the book does. Let's see. Let me check something quickly here. Do I want to do it that way? Did I compute this before? Let's see. Oh yeah. So one option is like, let's do it like this because it will be useful. It's a useful trick to keep in mind in your toolkit, as we'll do in a couple of minutes once we talk about the Gaussian. So option one to find this is to use integration by parts. Option two is the elegant option. Okay. So this is going to be what? Yeah. This is going to work. Okay, yeah. Wait, give me a second just to see if I'm not going to do something silly. But I think it will work. Just need to check it before writing it out. So this is going to be lambda plus 8 minus lambda x. Okay, and then this is that. Okay, yeah. It is going to work. Yeah. So yeah, I'm sorry about that. I like this method. So I just wanted to double check that. Yeah, it was fine. So you want to find this. I want to find this without using integration by parts. First, like since lambda is a constant, I'll take it outside the integral, right? And now I'll do something that we kind of did a couple of times before. I can see this as some sort of derivative with respect to lambda. Is that making sense? That this is the same? Because if you take the derivative with respect to lambda, with respect to lambda, right? You get e to the minus lambda x times the derivative with respect to lambda. So that gives you minus x. So if you multiply by a minus sign, you just get x. Is that okay? So the cool thing about doing it this way is that yeah, I think that's sometimes, yeah, I believe that's what goes under the name the Feynman trick, correct? Uh, does that appear in Oppenheimer's movie? I don't know. Yeah, I think it's like in like, because Feynman, I think they do like a camp, like, there's someone who plays Feynman in that movie. although I haven't watched it, so I don't know how much minutes they gave to him. Yeah, but I think it's known as a Feynman trick, correct? It's a cool trick to have in mind. So this is the thing, like the nice thing is that since this is a derivative with respect to lambda, actually you can take it side. I mean, there are like things that you have to be careful in general when you switch an integration with an integral. So, sorry, a derivative with an integral. It's not that you can always do it, but like here, like the fact that it's exponentially decaying and other things will allow you to do that. So you can take out the derivative with respect to lambda. But what we had seen that this was 1 over, didn't we compute this before? We had computed this before, right? We had computed that the derivative was 1 over lambda. Or let me put it like as lambda to the -1. Okay. So yeah, we did this before. And then, yeah, when you take the derivative, it's minus lambda times minus lambda to the -2. The minus cancel out, and you get lambda to the -1, which is 1 over lambda. So that's another way to find the expected value with the derivative trick. That actually would help in this case to find a similar trick will help you find the variance, which I'm about to define, instead of if you want to avoid the integration by parts technique. Yeah, so I think this is called Feynman's trick, correct? Oh, which brings me to, because someone had asked me, I don't remember who asked me last time about this terminology for the moments. Yeah, it's not sure how obvious it was anyways, but it's just like if you look at definition for, sorry, if you look at these definitions for the for the expected value, if you replace this pi with mi, where mi stands for like the mass of a particle, then this is kind of like the center of mass of that part of like a system of a collection of particles. And the variance, if you replace pi with mi, is kind of like the moment of inertia. So it's just like under the replacement of pi with mi, it just you recover like the formulas for the center of mass and the
Oh, yeah, that makes sense.
yeah, no,
Yeah.
it's kind of like one of those things that you kind of know, but unless someone says it explicitly, you don't see it. But yeah, it's kind of makes sense, right? So it's just like, yeah, you have to formally you replace pi with mi for mass of the ice particle, and then you recover like the formulas from physics. So yeah. So I can make it as a remark. If you take xi as sum of pi and xi, and you change this with mi, this is related to the center of mass. And then the variance would be related to the moment of inertia. Or like second moment. Like, I mean, again, like they're not that different, but yeah. With respect to the center of mass. Okay. But yeah, this Feynman trick, it will be useful basically right now. So the last thing that I want to say before moving to that is like that there's like a second moment formula and a formula for the moment of inertia. So there's like a formula for the nth moment, like, so the nth moment is going to be e of x to the n is literally just x to, like the integral from -infinity to infinity of x to the n f of x dx. And everything else like kind of works in exact, I mean, of course, whenever you write these formulas, you are assuming that the integrals converge. If the integrals do not converge, I mean, I guess you can just say that the moments are like indefined, ill-defined, or infinite, right? Like here, you do have to be a little more careful because they may not always exist, right? Since the integral is an improper one, right? I mean, they could be finite integrals if you, depending on how you define f of x. So it's not that many situations they do exist. In the situations that we care about, they do exist. But I'm just saying, like, as a rule of thumb, it's not that they always are forced to exist. And then the variance is the same story, is the expected value of x minus mu squared, which ends up being the same as the second moment minus the square of the first moment. The formulas are essential, like the derivations of these are essentially the same as what we did on Monday. It's just that instead of like a sum, you do it for integrals, but like the properties that you had to use are essentially the same. So nothing changes. And then you can define the standard deviation as the square root of the variance. And then sigma continues to be the standard deviation, which is the square root of the variance. Okay. Again, provided that this provided that all of this exists, right? But again, in most applications, especially for a course like this, which is more on the element, like, it's not super advanced, like all of these things will, for the examples we will do, they will all like kind of always exist. Okay. So again, if you want to check for yourself, so it's on the book, but it's not too bad to do. So you can check that for F uniform. The variance, I had already given you like the formula for the expected value, the variance, like, yeah, I have it here. The variance ends up being just b minus a squared over 12. And then for the exponential one, that we have been discussing, this one, lambda e to the minus lambda x for x positive, non-negative. The variance, like, again, is somewhere in here. It's just 1 over lambda squared. That actually can be found more easily with the Feynman trick if you don't want to kind of do integration by parts a couple of times. So the variance can be used with the Feynman trick. It's just like you need to take a second derivative with respect to lambda. I think that's the only thing that changes to find the second moment, because we already have the first moment. So you can try it with the Feynman trick if you want to practice it. Is that okay? So far, so good. Questions about this? Okay, so because now we're going to get into one of the most important random variables, which are the ones that have like this Gaussian density function, or this bell curve function. So what I'll do first is kind of like do like a mini crash course on these Gaussian integrals. And then depending on how much time we have left, I'll motivate for you how they appear. But I think I'll just start with the computational part, just to have it ready to go. And then depending on how much time we have left, I'll tell you where they come from. But they're probably the most, besides the uniform distribution, because like that's kind of very natural. this is a top contender for the most important density function, and we'll see that it appears from different angles. It's good to know that there are like different points of view where you kind of see it show up. So there's like an entropy perspective that I'll tell you. There's also like coming from the binomial distribution when you take a limit you can get it from. So there are like different ways to get it, and it's kind of nice to understand like all those ways. So let's take a 5-minute break, and when we come back, I'll tell you all these things about the exponential function. Okay, so now we can start talking about this very famous Gaussian integral. So let's start there. So I'm going to choose a positive number k. And we're going to consider we're going to start with the same thing as before. This f tilde of x, which is going to be e to the minus x squared over 2k. Okay, so let me see. I actually had already plotted it on GeoGebra because I knew we were going to get to that part today. Okay, so it's convenient to, you'll see in a bit, it's convenient to just have this value for k hanging around. So this is like the plot when k equals 1, and if you start increasing the value for k, you kind of are like flattening the curve, right? Or what should be like spreading it out more. Maybe that's a better way to put it. And if you start decreasing k, right, like it starts actually concentrating more and more, you know, starts concentrating a lot towards like close to the origin, right? So that's, but qualitatively, they're all like kind of this bell-shaped curves or these like Gaussian functions that I'm sure like everyone has seen, even someone who has never taken like a math class, right? So that's how they look. And again, we'll explain, I'll tell you, depending on how much time we have left, a couple of reasons why this would show up naturally. But for now, we're just going to just play with it and see what sort of properties we find. Okay, so the first one is that this is a non-negative function, right? This is a non-negative function. So we are in the situation, and as you saw, like it decays quickly as x goes to infinity. You're squaring the x, so on both ends it's going to decay regardless of the value for k. So it is decaying, and it being like the reciprocal of an exponential, there's no question that it will converge to the improper integral. So essentially, what we have to do first is kind of find, we have to find the value of the improper integral, because once you have the value of the improper integral, then you can just you can just divide by that to normalize it and get a probability density function. So the first step is just to find the value for the improper integral. So step one, I'll show it for you. What I want to show for you is that this integrates to root of 2 pi k. Okay. So that's the first thing that we will verify. And this is also called like normal distribution. I should have said that as well. Or normal distribution. So I mean, it's just, regardless of the value of k, it's more or less always the same because you can always make a change of variables to kind of absorb k into the variable x. So the value of k doesn't play a big role right now. It looks more like of a nuisance, but it will be actually very useful in a bit later. So let me just do it for k equals 1 just to avoid clumsy notation. So let me do it for k equals 1. So I'll do it for k equals 1, case of k equals 1, everything like the rest is similar. Other values are similar. So let's call this I. I want to find the value for this integral, right? And I don't know if someone did it. You may have done that in multivariable calculus. Like if like the thing about that course is that you never have time to do things. But if you have time, like I'm sure like you would have been shown this because it's like a cool trick. Uh, Ironically, what's easiest is to square it. So you consider, to find this integral, I'm going to consider I squared. I squared is literally I times I, so it's multiplying the improper integral twice, basically. And here you would say, well, there's no way, how can that help you at all, right? It seems like you just square the problem, right? Like you increase the difficult. I mean, it's not harder, but because once you have one, like you would get the other one, but it doesn't seem like too useful, right? To do this. But like the miracle of like just changing the notation is so useful here because like on an integral, it doesn't matter what you call the variable. So instead of writing this with respect to x and with respect to x, we can keep one with respect to x and the other one with respect to y. So let me put it like this. Is that making sense? I mean that is just more like an aesthetic thing to do because like when you integrate, you're free to put any variable, the name of any variable of integration. The thing is like now since it's being considered as a function of, I mean as an integral of x and an integral of y, you can kind of recombine them using like this Fubini's theorem of all double integrals, or basically that you can when you integrate a double integral, you can integrate it in any order, so you can actually just combine these two. It's like these are like two iterated integrals, but they can be combined into a single double integral, which looks like this. Okay. It does work because like the function, the thing that you're integrating here, is kind of splits as a product of x, something that depends on x and something that depends on y. In general, you cannot split like in general, it is not true that if you have a function of x, y, then you can just multiply the integrals. But when the function of x and y is just like a product of something that depends on x and something that depends on y, you can do that. So what I'm trying to say is that I'm basically using this property that like the integral from a to b, c to d of f of x, g of y dy dx is like the integral from a to b of f of x dx times the integral from c to d of g of y dy. That is something you can do when the function is like the integrand is really just a product of something that depends on x and something that depends on y. It's not like a formula that probably you emphasize too much because it just creates more like opportunities for people to misuse it. So, but it does work when the integrand factors out as a product. Okay. And okay, we're almost there, done. What should you do next? This looks very suggestive, I think, at this point.
Switch to polar coordinates.
Yeah, you just switch to polar. So this is in polar, this integral is taking over the entire plane. So the theta will go from 0 to 2 pi. And the r goes from 0 to infinity because it's the entire Cartesian plane. So in polar coordinates, remember dy dx becomes r dr d theta. And this just becomes e to the minus r squared over 2. That's why the factor of 2 is convenient here, so that when you do like the substitution, when you do a substitution, you can the u sub the du is just r dr. So there's nothing that depends on theta in this integrand. So you can just say this is 2 pi times the integral from 0 to infinity of r e to the minus r squared over 2 dr. And you can check that this improper integral, I mean, again, you make a u sub, for example, u equals minus r squared over 2 if you want. And this will just give you 1. So that means that I squared, right? I squared is 2 pi because that's what we were computing. And so I, which is what you care about, is root of 2 pi. And once you know that, again, like the case when there's a positive, so again, this is when k was being set equal to 1. But if k is not set equal to 1, you can just, again, reabsorb it into like change of variable type thing. And so it is not too different from what we just did. It's just like too many factors of k lying around. Okay, is that making sense? Are there any questions about this? Is that okay? So what that means is that you can, if you just take the function that we started with and divide it by its value of the improper integral, you will get a probability density function. This is called the normal distribution. So you can define the normal distribution, which is f of x equals 1 over root of 2 pi k e to the minus x squared over 2k. Is that okay? So far, so good. Questions about up to this point. So this again, the division is just to make it integrate to 1. So it's a rescaling appropriate to make it integrate to 1. But qualitatively, it doesn't like for a fixed value of k, it's just like a constant in front of the function. So it's not like affecting like the qualitative features of how the function looks like or things like that. Is that making sense? So that's a normal distribution. And once you have the normal distribution, the first thing that you want to know, once you have like this is characterizing like a random variable, and then the first thing that you want to know is its expected value and its variance. That's like the first thing you like. Those are kind of like, again, like the two most basic quantities that you can get out of an random variable. So let's try to just check what they are. Like in fact, the expected value is not too difficult. What do you think they should be?
I don't know what the exact value is, but you could definitely use a U substitution here.
But it's like an overkill because it is it is like the property of the integrand, because this is symmetric with respect to x goes to minus x, right? This is symmetric across the x-axis, right? But how about x? There was a name for this.
Rounds.
It's odd, right? Like the entire thing is odd. an odd function of x, right?
Then it's just 0.
Yeah, it's just 0. So it's
Okay.
like it's an odd function. I mean, of course, these are improper integrals. You kind of have to be a little bit more careful. But it's like, especially for something with exponential decay, it's more or less it works. Something that is exponentially decaying, for all purposes, it's like almost as if you were working on finite intervals in terms of like using the properties for integrals. Like the exponential decay is just like such a powerful condition that like you almost have nothing to worry about whenever you see it. So this is like an odd function of x. Remember, an odd function just meant that like, g of minus x is minus g of x. So whenever you had like an odd function, probably you saw that in Calc 1 or at some point in your lives, that will give you 0. Is that making sense? So the average value is 0, which is also when I mean, there's a version of the bell-shaped curve that is translated so that the average value is not 0. But I'm kind of starting with a more simpler one right now. So that's why if you remember the graphs that I was showing you in the GeoGebra, they kind of all peaked at the origin, right? Like it seems completely symmetric from with respect to the x-axis. So that's kind of why the average values were 0. Okay.
So this is the standard normal distribution,
Right.
right?
This is what is well, once I take k equals 1, it would be the standard one. Yes. The standard
Yeah,
one,
okay.
yeah, the standard one has like mean 0. So we already have that. And it has standard deviation 1. It's just that again, the only reason why I'm doing this slightly more generally is because having this k around is convenient to do like this Feynman trick again. If you don't put the k, you cannot do the Feynman trick. So it's kind of useful because of that. But if not, it includes what's called the standard normal distribution. Yes, the standard one being with k equals 1. So in fact, like you could like do this like an extension of this, which is what do you think would be the odd moments? We never computed them, but what would be the odd moments, like just based on what we were just saying?
It would all be 0.
Yeah, they all vanish. So yeah, because it's odd integrand again. So for the Gaussian, like that's also nice. I mean, again, you can shift this again. You could shift this if you want. So to do it when the mean is not 0, but especially when the mean is 0, it's very easy to see that this is just like an odd function. So all for the Gaussian or for the bell curve, for the normal distribution, all the odd moments vanish. So that's like a reason why it's nice to work with this one first. And so if, for example, if you were after something like the variance, right, which again, the variance is nice. So the variance of x was e of x squared minus e of x. I mean, I don't know, when I say it, I don't think it makes a difference in the words that I'm using. What I'm saying is that the variance was the second moment minus the square of the first moment, right? The first moment is odd, so it vanishes, right? So the variance in the normal, for this symmetric Gaussians is just the second moment squared. Sorry, it's e of the second moment, or the second moment. So many silly terminology. So for these Gaussians, is once you have e of x squared, then you will have like the variance. So let's just try to find that. So what is this in our case? This would be okay. This is going to be like the integral of 1/√2 pi k of the integral from minus infinity to infinity of x squared, right? Times e to the minus x squared over 2k dx. Is that making sense? So that's the that would be the formula for the variance. Now the thing is, as I was saying, if you look at the book, or more like the standard probability textbooks, what they will always just do is integration by parts. You can do it more elegantly using the Feynman trick. So let's just try to do it with the Feynman trick. So in the Feynman trick, is actually is very nice. You can start from this formula that I had written here. I mean, there are other ways to motivate it, but let me start here. This we had already found, right? We had already found this formula for the value for this integral. We already knew this, right? So we already have this. And so in the Feynman trick, you just differentiate both sides with respect to k, because why not? With respect to k, not x, right? There's no x anymore in the sense that this cannot depend on x because it's an integral over x. So like the function, like the x gets wiped out after doing the integral. So this is really only like an expression of k. So this is why it only makes sense to differentiate this with respect to k. Okay. And again, there's not too much to be scared about in this case because everything has an exponential decay. Otherwise, you can get in slightly messy territory, but you can kind of move the derivative inside the improper integral. And the other one is easy to do, right? Like it's just, I mean, this is like k to the 1/2, so it's root of 2 pi times 1 over 2 root of k. And then, I mean, this one is not, this is not too bad to differentiate with respect to k because this is kind of like k inverse, right? So you're taking the derivative of a k inverse with the chain rule. So this just gives you, it actually, because of the chain rule, you end up getting like this factor coming out, right? So you get, I mean, well, I'll write all of it to not go too fast. That's basically what you get from the chain rule, right? It's like the derivative is the exponential itself times the derivative of the inside with respect to k. But the inside is like this thing. Also, when you take the derivative with respect to k of this, like this minus cancels this minus, and this becomes k to the -2. So you just get the integral from minus infinity to infinity of e to the minus x squared over 2k times x squared over 2k squared dx equals root of 2 pi times 2 root of k. Is that okay? And oh, sorry, what are we talking about? What when you say is it just k, which part are we talking about? Is it just k?
Oh, I meant like I meant like and the
Oh,
result.
the total. Oh, I see what you're saying. Like the second moment you're asking me.
Yeah.
Yeah, no, it's going to be just k. Correct. Yes, yeah. So
Oh, okay.
yeah, but it's not maybe super clear. You have to first move this. Oops. Yeah, to see that, move this to the other side, right? Because and so
I
and
thought I got something wrong.
and then just move this to the other side. So you get the integral from minus infinity to infinity of x squared over root of 2 pi. Well, you can put like, yeah, you can put it like, I mean, you want to keep like a root of k as well here because that's like the only, because if you remember the probability density function, it had like a root of k in the bottom. So you put something like this and yeah, this will give you okay, that should be fine. Is that okay? Let's see. Yeah, because these two can, okay, so these two cancel these two. I'm moving this root of 2 pi to the bottom, and then I'm just kind of like, I'm just splitting like this k squared as I'm just writing k squared as k times root of k times root of k. which looks like kind of silly. But like, so one of these cases is like the one that you see here, and then one of these case I keep here, and the other k root of k I used to simplify it. So I mean, yeah, it's not. I mean, it's a little bit of algebra, arithmetic, but it is not such a bad arithmetic thing. Okay, is that making sense? So yeah, this is precisely the formula for e of x squared. So that means that for the normal distribution, so the variance, this is like the other important result of today. So the variance of x is e to the x squared, which is just k. So that means that k, the variance, remember, was sigma squared, like the standard deviation squared. So this has to be sigma squared. So that means that the k is actually the square root of the, I mean, it's the square of the standard deviation, or sigma equals square root of k. That's sometimes how people will write this normal distribution. So typically one way to write this is like, if you do this change of variables, if you write it in terms of sigma, the way in which the formula looks like is 1 over root of 2 pi sigma e to the minus x squared over 2k, but 2k is 2 sigma squared or something like that. So that's like another common way of writing the normal distribution. But you see, it is like the cool thing about this trick is that even if you wanted just the value for the normal, the value of even if you just wanted the value of these variances for the value of k equals 1, it's kind of convenient to keep k as a parameter, because then you can take the derivative with respect to k. If you remove k from the formulas, if you had plugged in k equals 1 or k equals 2 or k equals 4 from the very beginning, then there's no k to play with to take the derivative with. So it is a useful trick because you can just like do this differentiation. Otherwise, you're stuck doing what the math probability textbooks do, which is just like do like a very tedious integration by parts. Is that making sense? And in fact, there's basically you can use this differentiation trick, keep doing this, and that gives you like a formula for the even moments, which we won't use, but it's kind of nice to at least write it. So with this Feynman trick, you can find the even moments. You can find the even moments pretty easily. And you get, I mean, this is a baby version of what's called the weak theorem. That the expectation or the even moments is just what? K to the m times the double factorial of 2m minus 1. And I have to tell you what the double factorial is, because I don't think we have mentioned it before. So what's a double factorial? So this 2m minus 1 factorial is called the double factorial. So in general, what is in general n double factorial is just the product of the positive numbers up to n with the same parity as n. So I'm about to give you some examples. So for example, 7 double factorial is 7 times 5 times 3 times 1. You skip the even numbers because you're just supposed to multiply the numbers with the same parity. Or 8 double factorial would be like 8 times 6 times 4 times 2. So that's what in this case, obviously, for m equals 1, which is the one that we just computed, right? Like, because e of x squared, you plug in m equals 1, you get k, right? K to the 1 is just k, and 2m minus 1 becomes 1 double factorial, and 1 double factorial is just 1, right? So that's why you just get k. I mean, these, of course, once I give you the formula, again, with the Feynman trick, it's not difficult to prove, but otherwise, like once you have like an idea what the formula should be, you can prove it using induction or other things, like, which is like maybe less elegant than the Feynman trick, but it could also be proven that way. But yeah, I think the Feynman trick is probably the most elegant one. You just have to keep taking, instead of doing like the first derivative with respect to k, you have to consider like the mth derivative with respect to k. So, and that's how you keep accumulating powers of x squared, by taking more derivatives. So it's a cool trick to have. Is that okay? Is that making sense? Questions up to this point? Okay. So now, once we have a little bit of knowledge about this normal distribution, the first question that you could ask is, where does it come from, right? So, I mean, that's probably where you would have started with anyways. So where does it come from? So I'm going to give you two places where you can find that it comes from. One is kind of fun, which is like, again, like the continuous version of the binomial distribution. So like the first way to get it, but probably we'll do this one next time, because like the limit process is a little bit tedious. You have to use something called Stirling's formula for approximating a factorial. So it's a little bit more like a longer thing. So like the first way to get it is by taking the continuous version of the normal of the binomial with random variables. So it's like some sort of a continuous version of the binomial variable of the binomial distribution. The binomial distribution, if you remember, was something like that the probability of x equals I was what, like n chooses I times p to the I, q to the n minus 1, n minus I. I think I got it correctly, right? When you were doing n successes, I mean n experiments, and you're counting getting I successes. So again, we can start with this one next time, and I'll show you how you can get to the bell curve or this Gaussian distribution from that. You just have to take the limit in a careful way. So that's a little bit more tedious. So the one that's a little bit faster, because I'm just was going to skip a couple of points because we don't have like really the appropriate tools to go through all of it, is by doing this entropy principle. So the second way to get to this Gaussian stuff is like by maximizing the entropy. So second approach is to maximize the entropy. So this is why sometimes this distribution is called the equilibrium distribution, because that would correspond in thermodynamics to the distribution that characterizes like thermodynamic equilibrium. So this is called when you do that this way, it's like the Boltzmann-Maxwell distribution. So like if you remember, like the formula for the entropy in the finite case, the formula for the entropy was just minus the sum from I equals 1 to n of pi log base 2 of pi. In the continuous case, it is actually more subtle than what you would think, but that would take a little bit of a detour. But in the continuous case, the entropy, the easiest way to define it is as minus the integral of fx times the natural log of f of x. I mean, you could still do it in terms of like the log in base 2, but like for continuous random variables, like the natural log is more natural because that appears more like in physics applications. Like when you do natural log in base 2, it's because you're thinking more like computer science or electrical engineering, where you're doing more like communicate discrete channels, like communicating a message, like kind of cryptography, those types of things. But in the continuous case, it is more common to think about in terms of physics. So in physics, like the natural log is more common than like log base 2. So in fact, like it's kind of like a weird name for, like, instead of bits, you call them nats. That's like the unit of measurement in this case, like measure in nats instead of bits. But again, you can just qualitatively, it doesn't change too much. Okay, and then yeah, so just to tell you what happens, basically what you're trying to like the idea is that the Gaussian distribution, this one, root of over 2 pi k, right, is a distribution, is a probability density function with the biggest entropy, is a PDF with the largest entropy, amongst all the PDFs with the same standard deviation. So what I'm saying here is like you kind of have to look at all the probability density functions that have a known variance. So you look at all the PDFs probability density functions with a known variance, and among all of those, the entropy is the one that the entropy is maximized for the bell-shaped curve. So you kind of, in this, it's similar to what we were doing before with the discrete case when we knew the expected value. So here, instead of knowing the expected value, you know the variance. So among the ones with known variance, the entropy is maximized at the bell-shaped curve for the normal distribution. So again, I will just finish telling you the story quickly because this does go a little bit over what you're supposed to do in this course. Because here in the finite case, like what you have to do is kind of like this Lagrange multiplier thing. In this case, you cannot quite do that. You have to do something that's called like the calculus of variations, because like you have to take a derivative with respect to a function, not a variable. So like usually you can take the derivative with respect to x, right? You have seen things like this, but there's like a thing called like a functional derivative which allows you to take the derivative with respect to a function. So it needs calculus of variations to take to do something like a derivative with respect. I mean, this is not quite the notation that is given to it, but it's kind of like a derivative with respect to a function, not like just x. Once you have like a machinery that allows you to do that, it is like a Lagrange problem. So it is like a Lagrange multiplier problem. And so you end up like there's like a long story, but you will end up with something that looks like, where do I have it? You end up something like the f of x must satisfy uh ln of f of x plus 1 plus lambda 1 plus lambda 2 x squared equals 0, where lambda 1 is kind of like the multiplier, like the Lagrange multiplier for the first constraint. So this is like the first Lagrange multiplier, first like Lagrange constant or multiplier, coming from the constraint that the probability must integrate to 1. And lambda 2 is kind of like the second Lagrange multiplier, coming from the fact that the variance is known. Coming from the second constraint. So there's like a second constraint in this equation because you are working with all the probability density functions for which this quantity is known. I mean, implicitly here, I'm taking their average to be 0 as well. That's not much of a restriction. So I'm just saying that once you do that, you can show, like, again, I don't want to go over, all these details are fun, but it's kind of like a little bit more complicated than what you need to worry about. So you can show from this that f of x has to be like e to the minus lambda x x squared over lambda 2 over e to the lambda 1 plus 1. So this already looks like a Gaussian, right? And then the values for lambda 1 and lambda 2 are found from the constraints. So, and then lambda 1 is found from lambda 1 is found from the first constraint, and lambda 2 is found from the second constraint. And so it does end up looking like essentially like the normal distribution that I just wrote, but it is a little bit way more technical than what we were doing in the finite case. But it is kind of useful to know that there's like this entropy principle still for like the continuous case, which is some sort of like uncertainty or lack of information. And the normal distribution is in a sense like the distribution that it maximizes the uncertainty among all distributions with the same variance. Okay, so it is in that sense like it is a default of choice once you know the variance, because like again like the entropy principle says that you must always choose like the distribution with maximum entropy, because it's like kind of like the most fair option to choose. So it is like still nice that and it does match. This will match the distribution functions called the Maxwell-Boltzmann distribution. If you think of x as the velocity of a particle, then if the x is like the velocity of the particle, right? Let's call it v. So what does it mean for the variance to be? What does it mean for the variance to be fixed? What function of the velocity do you know depends on v squared? What's a quantity in physics that it uses v squared, like the velocity squared?
The kinetic energy?
Yeah, it's just basically like kinetic energy, correct? So if you have like a gas of non-interacting particles, where you can assume like the potential function is 0 or vanishes, like unless there are collisions, the energy is more or less like the kinetic term. So this is roughly the kinetic energy or the total energy of the system. So it is kind of saying among all possible distributions for the velocity of a particle, if you know the fixed average energy of the gas, then the distribution must satisfy this normal distribution, and that's like kind of like when Maxwell found, that's why it's called the Maxwell distribution. So f of v kind of looks like e to the lambda v squared over e to the lambda 1 plus 1. It's just like later you can identify this lambda 2 with kind of like roughly like the inverse of the temperature. So, and I mean, the lambda 2 gets like a physical meaning in terms of the Boltzmann constant and the temperature, but it is essentially like the distribution Maxwell had found. So, but like you see, like the variance kind of has like a very clear physical meaning if you think of x being as the velocity, because the variance is like squaring the velocity, so that's related to the kinetic energy. It's just like for these ideal gases, you kind of ignore the potential energy term. So like the energy is more or less like the kinetic term. If you assume that the walls are perfectly elastic and things like that, so that no energy is lost and things, so that you have conservation of energy. But it's basically I mean, again, once you kind of dress this up a little bit better, this is essentially like the distribution in physics that characterizes like the ideal gas law or things like that. You can from there you can start re-deriving all of like thermodynamics basically. So, and it's just like the maximum entropy principle. What Boltzmann did more or less was kind of to like give like a statistical interpretation of the entropy. Like the entropy had been defined before like Boltzmann, but he kind of was like the first one who put like on solid grounds this idea of identifying entropy with like some sort of like with this like you know with in terms of this a statistical interpretation of like taking like the logarithm of the probability density function. So yeah, well, it's a long story, but it kind of goes like that. So yeah, so it's like it's a fun thing to know that it works this way. What we'll do next time, which is a little bit more down to earth, and it's kind of a fun calculation, is to do it from the binomial distribution. So that will be nice to check, because it does have like a more down to earth flavor. This is a little bit overkill, but it's kind of like the most elegant way to get it. And this will be the same distribution that appears in what's called the central limit theorem, which is one of the two biggest theorems on probability, together with the law of large numbers, the two of which we'll talk, I don't know, like maybe in 2 weeks from now or something like that. So you'll see, that's why it's called normal distribution, because it's kind of normal to run into it, right? And you'll see it's kind of like the go-to distribution. So yeah, but I think it's a good place to end. So I'll try to send you today like the list of problems for the quiz, and I'll also send you today like some sort of study guide for the exam on Monday. So if that sounds good.
So I have a question.
Mm-hmm.
So what chapters are coming out for the test?
Oh, it's
Like,
only
is the
it's
entropy thing gonna be coming out?
well, it was only chapters 3 and 4. It doesn't include anything of the continuous stuff that we're doing right now. I may put like a silly question about entropy, like more like kind of, I don't know if you remember when we computed the entropy of a Bernoulli random variable.
Yeah.
Something like that. Like, I give you like a random variable, something like the problem in the quiz, which was like, what's the information of an event where the event was kind of like getting a 7 on a pair of dice or something of that sort. So
Okay.
something very like just down to earth, where you just have the probabilities, you plug it into the formula for entropy. I won't ask anything that kind of goes to the level of detail of like solving a Lagrange multiplier problem with the entropy stuff. Except maybe for like this one, which I also had put on the quiz, where like the first probability was constant. I don't know if you remember this one on the quiz. That the first probability was known. Sorry, the first probability was known. So you use the maximum entropy principle to say that all the other probabilities had to be the same as 1 minus p over n. 1 minus p1 over n minus 1.
Yeah.
So something very, very kind of silly, very easy. Yes, but nothing like too crazy with this entropy. But yeah, like I probably put like at least one question about entropy, where is it computing it or like doing like a very simple Lagrange multiplier problem with it. But it's only the discrete version. There's nothing that would be on the continuous stuff that we have been doing.
And also like the random variables that were not taught, like the hypergeometric.
I think
Those are not gonna come out, right?
So they wouldn't come out. I'm not sure. Like, so which ones did I did? I did a geometric, the binomial. I think there was one
Negative binomial.
negative binomial, and yeah, if I didn't, I don't know.
Poisson.
Uh-huh.
Poisson.
A Poisson, yeah. So, but for those, as I said, there's so many formulas that I'll probably put the formulas on the test without saying which one is which. So you just have to recognize them, but you wouldn't need to memorize them. But yeah, I wouldn't like. There's just like so many random variables that if I didn't mention like hypergeometric, I would have to check. If I didn't say it, then yeah, you don't. I wouldn't ask it. I wouldn't ask about it. Like the problem usually won't say, oh, like depending on the type of a problem, it's more like you have to remember, oh, the binomial is used for this kind of situation, the geometric is used for this kind of situation, negative binomial is used for these kinds of situations, and then you just recognize it and then can use whatever you need to use. But yeah, if I never went through the hypergeometric, then yes, I wouldn't ask for this.
Cool.
Yeah. Is that okay?
Yeah.
But I'll give the formulas because like there's no way to memorize all those formulas. But I just won't say which one is which. So you do have to remember how to recognize them, in which context they get used. But only I'll give the ones that we saw in class, not any others. Yeah. Did you have any other questions or?
I'm not sure if you have discussed like the one you said that the first probability is constant problem thing.
Oh yeah. I actually solved it. I think it's actually in the PDF. It's just that I had done it last time in class before doing office hours. Let me see if I can find it. I can show it to you. Oh, here it is. Can you see?
Okay.
Do you see it? Oh, like now I'm trying to find the PDF. I have like 10 PDFs open on my computer, so I don't know where it is. Oh, here it is. Yeah. So if you go to the probability part 2 PDF, it starts like around page 120. So it's just that once you know that P1 is constant, right? The easiest way to deal with that is just call it C for constant and think of the entropy as a function of n minus 1 variables. So just get rid of P1 completely. So the entropy just becomes this, right? But again, this kind of corresponds to the constant term. And then the constraint, which was like the sum of all the probabilities equals 1, you kind of like can break it into the part related to B1 and the remaining ones. So the constraint for the remaining n minus 1 variables is just that the sum of the probabilities should add up to 1 minus C. Is that making sense?
Yeah.
So that nice thing about doing it that way is that instead of having like two constraints, like you kind of explicitly got rid of one of the constraints. So it's like a Lagrange problem just with one constraint, which is a lot easier. I mean, the other one wouldn't have been that much harder, but it's just more annoying. And so that's how you get all the probabilities have to be equal to one another from 2 to n. And once you plug that back into the constraint, and then you get that P, like all of them had to be 1 minus P1 over n minus 1. Is that okay? Yeah. So yeah, something like that. Yes, I feel like that's not too bad, and it's a nice application of the Lagrange technique. Something like the one that we had done in class, where it was like where I had fixed the expected value. No, because like it doesn't allow you to give like a very explicit formula for like the answer for the lambda 1 and lambda 2. So it's kind of like an unfortunate thing. And I mean, I don't see the point in like, just solving an equation like on Wolfram alpha with an approximation or whatever. But something like this, yeah, this is kind of elegant and not too bad. So, yeah, something like this is okay.
Okay, so this is like not about like the quiz, but about like the lecture just now.
Mm-hmm.
So just now you mentioned that the odd order the odd order
Moment,
moment,
right?
yeah, of like the normal distribution is what, 0?
Correct. Yes.
And I noticed that it doesn't really matter if it's a normal distribution or not.
Oh well, it.
Like
Oh,
as long as it's symmetric about
correct. Yes. Yeah. Yeah.
the origin, right?
That's true for all the right. That's true for any value of k, right? Because all the ones that I wrote today were symmetric with respect to the origin. If it's not symmetric with respect to the origin, right? If there's an expected value, the odd moments do not vanish. What vanishes is what's called like the centered odd moment. So it's kind of like e of x minus mu to an odd power. So you have to it's kind of like cheating, right? Because you just shift the odd moment instead of like making it around 0, you make it around mu, and then they do vanish again. So, but yeah, the k, the value of k didn't matter in this argument. So, uh, that's correct. It does work for as long as it's center, and when it's not center, to fix that, you just like compute the odd moment with respect to the about around the mean instead of like around 0. Is that making sense?
Yeah.
Yeah. So yeah, it's like a cute thing to know. Yeah. So it's like only the even powers of the moments matter for the normal distribution.
So yeah, I mean, as long as the moment exists, like the odd
Right.
order moment exists also, right? Yeah.
Right. Like the thing is like again, because the normal distribution is literally like an exponentially decaying function, there's no way, I don't know if you remember these L'Hopital type problems where like an exponential function defeats almost anything you can think of, right? So an,
Uh-huh.
an exponential function grows faster than a polynomial, an exponential function grows faster than almost like other like natural calc 1 functions. So since you're integrating like a polynomial, which is x to the n, against a negatively decreasing exponential, like that just gets rid of everything. So it just there will never be any convergence issues when you're just integrating like a polynomial against a decreasing exponential. There's like just like, so it just goes to 0 so quickly that yeah, it's like it's kind of like almost the best convergence you could ask for, like for an improper integral. That's the other reason why you can do these things about moving the derivative with respect to k out inside or outside the integral, because like in general, they're like, if you wanted to go this so rigorously, they're like, you have to justify that you can change the order of integration with differentiation and things like that related to absolute convergence and other properties. But with an exponential, it's kind of like you're good to go. It's like really, there's almost there's no way to get lost. Like you can kind of manipulate it in the most naive way, and you're safe. So, but yeah, in general, if it were like something else, then you have to make sure that the integrals exist. Blah 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 blah. Yeah.
So, but how does it make sense that an expectation does not exist? Like if I have
Oh
a
well,
set of numbers,
yeah.
and when
Uh,
I always be able to find its expectation.
no, it's like sometimes you can have, okay, it's like kind of, you can do like, what you can put, like you can integrate something like 1 over x squared plus 1, right? Think about like
Uh-huh.
the density function. Again, that's not the most natural one, right? But or something like maybe a little bit that converges quickly because it's an improper integral, right? So you want that. No, I think that one would be fine. If you take 1 over x squared plus 1, right? That integral from minus infinity to infinity is finite, right? Uh, I think that should be fine, because like
I mean,
you compare that to,
mathematically it makes sense, but
yeah.
intuitively it does not.
Well, like I'm typing it on the chat. You have something like 1 over x squared plus 1, right? Uh,
Uh-huh.
I'm pretty sure that if you that's our tangent, right? Like the integral for that, right? So
1 over x squared plus 1.
yeah, like the antiderivative is our tangent.
Yeah. Arc 10 or something, is it?
Yeah. So like that integral should be finite, right? It gives you like pi or pi over 2. I don't remember, like depending on how you define things. I would need to double check. The point that I'm trying to make is that this will define a probability density function after you renormalize it, right? But if you look at the moments of this, like you start multiplying this by powers of x, right? And eventually the numerator will just become bigger than the denominator. So this will diverge. Is that making sense?
Uh-huh.
So think about
Ah,
think about like the fourth moment, like put something like the fourth moment. So literally it would involve like integrating x to the 4 over 1 plus x squared.
Uh-huh.
That will diverge. So yeah, it can diverge, but again, it's happening for something that may not be so natural, because why would you maybe think about looking as one of to 1 over x squared plus 1 as a thing to consider? But yeah, that can happen. So it is, I mean, it's not too bad to come up with mathematical examples. It's just, it may not be like, of course, like for physical problems and things like that, you kind of expect for physical reasoning that the variance has to be finite, you know? So it's not like you would just say, oh, this is like a physically unrealistic model, and then you just throw it out.
Yeah.
But for mathematicians, they exist. So it's like a different.
Yeah, because doesn't infinite variance means that there's like infinite distance between a point and the mean?
Well, it just
Like
means that
that's variance, right?
it just means like that there's a like yeah, that the average fluctuation is like diverges. Yeah, so it's kind of, I agree. It's not too easy to like physically it would not make a lot of sense in most situations to think that that would happen. But yeah, it's kind of like saying that the average error or average fluctuation around the mean uh, diverges, right? But I mean, that's what you get into, with improper integrals. It's kind of like these examples in Calc 2, like this Gabriel's trumpet or horn, like that had like finite volume but infinite surface area, things like that. You can just start constructing like counterintuitive things once you allow improper integrals. I'm just saying, for exponentially decaying things, everything is kind of like behaves basically as if it were like a finite integral. Like there's no crash with intuitions. Like it's all good.
Okay, got it.
Is that making sense?
Thank you.
Yeah,
Very
sure.
helpful.
Yeah, no problem.
Yeah, have a good night, I guess.
You too, you
Thank
too.
you.
Okay, bye.